Good day, everyone. All right, so this lesson, we are looking at directions of acceleration. Something that should be focused on more in textbooks, I find, because it's just a confusion point. So we'll look at the ways of working with and referring to and describing acceleration situations where we have different directions. Okay. Yeah. So there was a question in the previous lesson that had a negative result for acceleration. We'll be looking at that one as part of this. So basically, I hope you noticed that there's kind of an issue there where you have this negative answer and you might have been challenged to think about what that means. That was on purpose. So hopefully you noticed that, and now this is satisfy your curiosity and help you learn more about how that works, how to refer to it, and so on. So we saw in the past we have common direction systems: forward, back, up, down, things like that. And typically you're going to assign a positive or a negative to them. And soon we're going to have positive and negative equivalents in the math work, and that's starting today. Okay. So if you decided which direction is positive, up would be positive, so down would be negative, or forwards positive, backwards is negative, and so on. So adding in a negative to values changes the direction, of course, right? So if you had a statement like -4 meters listed as forward, so -4 forward, of course, would mean the opposite of forward. Okay, it means backwards. That's one thing to get under control right away. Okay, so this word doesn't necessarily mean the direction. The negative has the power to flip that in logically. I think that makes sense, right? So the question had an initial velocity of 14 and final velocity of 0, and the change in time happened. It was 5 seconds, and so it would have been calculated like this in that homework assignment. So you'd have an answer of -2.8 meters per second squared. All of these were forwards. That one's just gray. Basically, like it's implied that forward doesn't matter, I guess, right? There's no direction necessarily for forward, I guess. But anyways, they were forward directions, and so this is kind of a forward answer, but it's a negative, and so that would mean backwards. Okay, so we have a acceleration backwards, or really what's going to happen is we're going to think of this as in the opposite direction of the motion is going to be the end best result way of thinking about it. So the focus is about negative acceleration and what it means. In the above example, it meant slowing down, went from 14 down to 0. Would negative acceleration always mean slowing down? You might even call it deceleration, which is correct in this case, right? But as you'll see when we go through this lesson, negative acceleration, the answer is no to this, right? Does negative acceleration always mean deceleration? Does negative acceleration always mean slowing down? And the answer is no. Okay. So to start to look at this a bit, I'm going to use an applet called Gizmos, or it's explorelearning.com, gizmos.explorelearning.com. You can see these kind of things as a trial. It gives you like 5 minutes to play around with it. I have an account, so I can just take my time here. That's fan cart physics, they call it. And so I'm going to simulate situations where you have a velocity forward and an acceleration forward, and then you have a velocity forward and acceleration backwards, and so on and so on. Okay. So I'll be saying like velocity in the positive direction, acceleration in the positive direction, for meaning both of them forwards, and so on. All right, so here we go. Velocity forward, acceleration forward, both positive direction stuff. And so there's your positives, right? So if I'm going to simulate that, then I can go into my gizmos here. Got it, whatever. And I can have an initial velocity of something, maybe 1 or something. And I can have one of the carts on here, or one of the fans, sorry, on the cart. I can turn the fan on, and then I can press play, and I can watch the motion, and I can analyze the acceleration, and so on. Right now, we're interested in the VT graph, so let's get that ready as well. Let's go to the graph, and we're going to choose VT graph. Okay, and we're going to see what it looks like. So obviously, I'm setting it as an initial velocity of 1, so you should be expecting our start right there. And then every second, it's going to increase the velocity by a certain amount because it's pushing on it, right? So it's going to be constant acceleration. And so we can just press play and see the kind of graph we get. Okay, so it just goes down and stops. So this is, of course, the result, where we have velocity forward and acceleration forward. And of course, we can tell it's speeding up, right? And so this is just kind of setup I had just to be clear as to what it was and so on. This showed a DT graph and a VT graph. It's that one actually, I'm not sure. I'll just get rid of that one. I don't remember what that was. But this is, let's just go with the DT graph like I showed, right? VT, sorry, VT graph like I showed. So what about if we have velocity forward and the acceleration's backwards? In other words, we have a positive velocity but a negative acceleration, right? So I don't remember what number I used last time, but let's stick with the 1, I guess. Although if I look at a faster starting velocity, give me more time here, so I have to reset here. So that'll give more time, and basically I'm just going to change the direction of this. So we have a velocity, positive velocity, and a negative acceleration in this case. And so we're going to look at what that looks like. Okay, so we're going to look at the VT graph of it, right? And so I think it's pretty obvious it's going to be slowing down, right? So it's going to start at 2 and it's going to slow down to a stop. And I probably had a note here for myself, only let it go until it's 0 velocity, because we only want to analyze that one kind of motion, right? So let's press play there, and then pause-ish, right? I managed to pause just as it was stopping, that's essentially, right? So we have a negative slope, so it's a negative acceleration. All these things are self-consistent with what we've looked at so far. So it looks like that, right? So we set it up. Like I said, here you saw what I did. This is, well, I don't need to put that out there, I guess, but let me just shrink it down, I guess. Picture what's causing this motion, right? Motion forwards, the fan's pushing on it backwards, and we have the graph result, right? So we can tell that this negative acceleration is causing it to slow down. It's causing a deceleration, right? So, nothing's wrong with anything we're saying here. Velocity backwards and acceleration backwards. So in this one, we're going to have the velocity backwards and the acceleration backwards. So we're going to have an initial velocity. Oh, I have to basically press play now, right? There's no way to set up an initial velocity of a negative value in this program, but I can just press play and let it go, and I have a negative velocity and a negative acceleration. What's that going to look like? Well, we can press play and see that one, right? So you're going to see this kind of picture, right? So it's this section right here we're focusing on. So that would be like this. So negative velocity, negative acceleration. It started from 0, so whatever, it doesn't matter what I start from, right? But you see what's happening is it's speeding up, right? So if you were locked into thinking that negative acceleration means deceleration, well, that's not a great thing, right? Because in this case, it's not decelerating, it's actually speeding up. So this is an example where negative acceleration is causing it to speed up, right? So that circled section there is absolutely that kind of graph. Okay? And finally, velocity backwards and acceleration forwards. So I have to set this up again and basically turn the fan around while it's going backwards and manage to get to accelerate forwards. Okay, so let's reset here. I'm going to press play, and once it's going backwards, I'm going to switch the direction, but I have to do it early enough. Okay, so let's press, let's actually press play for a little bit. I'm going to give myself more time here by doing this. Okay, so right now it's going backwards, but accelerating forwards. So that section there, I just pause. This section right here was what was going on. And it was going backwards, but it has an accelerate. It has a negative velocity and has a positive acceleration. Okay, so the graph that we ended up with was like this. Okay, so it's this section here, this circle right here. This section here was the one we're talking about, right? We have negative velocity. We're in the negative velocity answer numbers here, but we have a positive slope. We have a positive acceleration. What's that causing? Well, that's causing it to slow down. So not only is negative acceleration not always deceleration, positive acceleration is not always speeding up. Right? So the safest way to think about this is just if the velocity and the acceleration are in the same direction, you're speeding up. And if they're in the opposite directions, they're slowing down. Okay. And certainly we have established here that negative acceleration doesn't always mean deceleration, and vice versa. And I could even add in plus, and I should say, because I have to use a plus symbol, and positive acceleration doesn't even mean, right? Doesn't always mean speeding up. And so there, obviously there's a bit to keep in mind here about this stuff, right? So Gizmos has little questions to do with this, so you can quiz yourself if you want here. According to the graph below, what was the initial velocity of the cart? That should be pretty easy. So it's going to be like the 0.5 number, right? So I guess we could go and do the quiz itself here. Questions. So 0.5 looks like. What do we have here? Acceleration of the cart shown below is represented by in the graph given. The second block is added to the cart. I kind of have to skip that one because we haven't done Newton's laws yet. Okay, so yeah, I think in my lesson file, I probably just don't have it captured in there. So I think I'll abandon ship because we can't strive for perfect on that quiz because we haven't done all that material yet. Which of the following cart configurations would produce the distance versus time graph? And so what I'm doing there is I'm reminding you of how you could get tangent slopes. And so this tangent slope right here, that value, that slope value would be this number right here. Right there, I guess, somewhere in there, right? And then this one would be this value, right? This slope here would be that value, and so on, right? Those numbers. We got the 0, so the 0 corresponds down there, and so on and so on. And then we have negatives, right? So negative velocity and then a negative larger velocity, and so on. So you'd have negative velocity and an even bigger negative velocity, and so on, right? So if it's a straight line, right? If constant acceleration, uniform acceleration is another way to describe that. Which situation would make that happen? Well, you can tell we started with a velocity forward. So all those have velocity forwards written on them, which is my handiwork there to clarify. And it must have been a fan blowing backwards to slow it down and make it go the other way, right? So it must be B. Right? It must be causing it to slow down at first. So negative acceleration causing it to slow down first and then to speed up once it turns around. So that should all be making sense, I hope, at this point. This example, we'll see how when we're working with the numbers, what that looks like. So we have a cart initially coasting up a ramp with a starting velocity of 6 meters per second, an acceleration due to the angle of the ramp that is going up, and gravity, of course, is 2 meters per second squared down the ramp. So a really common direction choice would be positive is up the ramp, like positive is up essentially, right? In which case, this is what we'd be saying. We'd be saying, oh, that acceleration should be counted as a negative 2 meters per second squared. Right? We could have described down the ramp as the direction, in which case we'd be using positive. But we'd also have to put, I should add to this, and even weirder, the velocity would have to be in as a negative 6 meters per second. And that would mean down, or that would mean up. It's messing me up right now, even trying to think about it, right? That would mean up the ramp. And I think you can appreciate how your brain will get kind of messed up by that positive negative inconsistency. Up is typically positive in our mind, so let's stick with that, right? So we have a velocity, a v1 of 6 meters per second. I don't have to put the positive in, and I typically don't bother putting the directions in either, especially here because I'll do it this time because, just for clarity here, but this is negative 2 meters per second up the ramp. And I don't know if I got to this. Yeah, I did that already, right? I'm just reminding myself when I looked over what I was going to do. I've already done that where putting the negative on changes the direction and so on, right? So just to remind myself and you of it. So this, remember this is equivalent to, so negative up, i.e. down, right? And then, this is understood to be a positive in here, which then if I had it up, it just means up, right? It's not, it's what it is, right? Not a confusion there to talk about, really. And then acceleration, what card is that? Oh, I was thinking there was a question to work on here, but this is just basically looking at how we assign variables for this and so on, right? So then if we're asked, like, how long will it take to get a certain final velocity, I'll make a question here. So how long will it take to end up with a velocity of 12, let's say? So it might have said, like, how long to double the velocity, right? So delta t equals question mark. So the question could have been, how long will it take for the velocity to, I can't do that actually because it's slowing down. So let's go 3. How long will it take for the velocity to get half, or do you want to go with 0? That'd be like, how long does it take to get to stop going up the ramp? Let's do that one. Okay, how long will it take to come to a stop? To get to the highest point it reaches. Okay, so we'll just that up there for now. So given this is a question. This is here, I guess. Yeah, so we can just do the question as well, right? Good practice. Mouse out of the way here. All right, so based on the information that is given, hopefully you're recognizing, analyzing that we have acceleration equals delta v over delta t. And so we have an acceleration of -2. And, we could put decimal zeros and stuff like that, but come on, like, we don't have to worry about that. Let's put in the delta v. Notice the delta v is equal to v2 minus v1, right? And so delta v is going to go in as 0 minus 6. It's going in as -6. In other words, the velocity decreased by 6. Okay, so that's sort of a first part of the question. I suppose maybe we might have done that first more officially, or we could have it in sequence here. So let's do it like that. Either way, you can picture doing this first or in sequence like this. So this would be the 0 take away the 6. And so we have -2 equals the -6 over delta t. So we're trying to solve for time. So we're going to multiply both sides by delta t and end up with -2 delta t plus the -6. So we're going to divide both sides by -2. And anytime you want to pause on a question like this and give it a try yourself, that's good active learning. That'd be a good thing for you to do, right? So you have the power to do that. Therefore, it would take 3 seconds to reach the highest point. So we're tackling a question using negatives appropriately and so on. Okay. All right. I guess I got ahead of myself here. I forgot that it's in the rest of it, but so let's keep going. So draw the VT graph of this thing until it comes to rest. Just basically following up with this, right? So the answer to this, of course, has already been calculated. So we'll just fill that in, copy it over or whatever. But basically, this is the question. This is what we want. It's down to 0, and we even have that it took. What was it again? Was it 3 seconds? So it took 3 seconds. But for now, in part A, the way this question is written, this would just be written as like, T2 or T or whatever, right? So not even really anything there. And really, this stuff was, like I said, I was just going to talk about the direction assignments and so on. Really, all this stuff belongs the way the lesson was set up down here. Wait, that stuff was a mess. All right. All right. So maybe I'll just clean this up a bit here and just change this to be like I was planning on, just basically talking about how we would consider our given information to be in terms of signs. All right. So we're back on track here. extend the graph until the cart reaches the starting location. Okay, so basically you should recognize now at this point that you have this initial velocity of the 6, and we are reaching the, I was supposed to get a 6 for some reason, I wrote an S. So this is our VT graph, and we're starting at 6. That's the initial position, start, whatever. And then we talked about how this is at the top, and then it continues on and eventually gets back down at the back to start, right? So if you're looking at where that would be and how long that would take and so on, at this point we can add in the 3 seconds there, which is extra info we have. And so something you can look at is that something has the same acceleration on the way up as the way down. It's going to take the same amount of time to get back where it started. And so really you can just be saying, okay, well, it's just another 3, right? So plus 3 is just a very logical thing to know. You can still calculate these things, but that should be just a very obvious thing that you can do. Okay. You could, of course, do this full on where you say, given v1 equals 6, acceleration equals the -2. How long until now, because I said back the way it started, I guess we'd be best to say how long until v2 equals -6. Soon, later on in the course, we'll be able to say instead of v2, we could say how long until the displacement is 0. In other words, how long till we get back where we started. And so that's going to be full circle. We'll come back to this and be able to tackle that kind of approach. But obviously here we'd be able to just say acceleration equals delta v over delta t, and we'd have a -2, and we'd have a delta v now of v2 minus v1 over time, and we just fill it out, right? So we'd have so v2 is -6, take away the original +6, and so we end up with -2 and -12. Integers here is just -6, subtract another 6, right? Down 6 and down another 6. So we end up with that. So we multiply both sides and divide out. And you can probably see what's going to happen here. We're going to be dividing -12 by -2. And we're going to end up with the 6 answer that makes sense based on the logic I originally described. Dividing by -2 gives us a 6 seconds, right? So this logic here of it being just another 3 seconds, because it's the same acceleration on the way down and so on, is confirmed, right? This should be true here, that it's that, and we're obviously confirming this. And again, I'm hoping we come back to this, that you're sort of looking forward to learning these new things. And so I could actually say, if we started with a velocity of 6 and had an acceleration of -2, how long until the displacement's 0? How long till we get back where we started? It's going to be a totally different approach, totally different looking work. It's going to spit out that same answer of 6. Okay, so we'll get there. This one, determine how long it takes to go down further down the ramp, end up going -14 meters per second. So in this case, we have given information still, right? I'm going to just basically point out, if we extend the graph further, then we have this new question, right? This new question that's circled in purple. If I can get this thing to delete for me. The circle in purple is basically, now we have this like starting velocity of -6, right? It's how much longer, from how long it takes. I guess I'm doing this as an individual question here, and then I could add the 6 onto it. Or if this had said, how much longer does it take to end up going, whatever, however you interpret it, right? But picture our given information now is I've got a v1, an initial velocity of -6, and then I want a final velocity of -14, and I've got an acceleration of -2. So now in this question, we're actually doing the math for a question where we've got a negative velocity and a negative acceleration. So they're both in the same direction, and it's causing it to speed up. Okay. So the math works out much like I've been doing. And so see how this ends up being a plus here, right? The integer work. And then Yeah, so we end up with a -8, multiplying and dividing and so on like normal, and we get a 4, right? So I would, in class, always do this, right? Should became a plus, that's why this is a plus now, and so on. Right, so the total time then, if you're adding it all up, would be the 6 plus the 4, giving you the 10. There's your paraphrasing, and so on. All right. So that's pretty much it. I do have one little thing to show, just to warn you about trying to learn from other sources on YouTube or Google or whatever else. This is a question from a site that one of my colleagues sent to me. It's like, oh, I saw this really good site. The school board's like recommending we use it. It was like, here's a good resource. Here's a question that came from this resource. Okay, what's the difference between positive and negative acceleration? And so I've added in choose a correct answer if it's listed. But really, it wasn't listed originally. Is the spoiler alert here? So positive acceleration applies to fast objects. Right away, I'm like, no. Positive acceleration occurs when the object speeds up. Negative acceleration occurs when the object slows down. That's probably the one they wanted, they thought was right, but that's not right, right? Because positive doesn't always mean speed up. Positive acceleration applies to objects traveling on Earth and other ones in space. No. Positive acceleration expressed in meters per second. No, that's not even correct because it's meters per second squared. Negative acceleration expressed in kilometers per hour, definitely not, right? And so really the answer should have been an option. What answer should have been an option? Group this apparently. Really, they should have just said they're in opposite directions. It's so easy to answer that, really, right? It should have just been they're in opposite directions. Oh, it's already there in red. Oops. Right? The answer that should have been an option, they're in opposite directions. So it's just a common mistake that people make if they're just not quite on top of the physics concepts like they should be if they're making a resource to do with physics. So my apologies on behalf of the world. Misinformation is everywhere, unfortunately. So you got to be careful what you commit to your knowledge. Think about it critically. Whatever. This question in this set was actually much better, showing knowledge of what I just talked about, right? Which of the statements is true? Acceleration in the direction of motion slows you down. Be like, nope. Acceleration in the direction of motion speeds you up. That is true. Acceleration against the direction of motion has no effect. Definitely not. That's going to slow you down. Acceleration in the direction of motion against the direction of motion speeds you up. No, it's going to slow you down. Right? So this one's true. And so that's along the lines of what we talked about in this lesson. Whereas this one was just, it should have been along the lines we talked about in this lesson, but they got it wrong. And that happens. I make mistakes too. So here we go. This is questions. I want you to draw VT graphs for all of them. It's not hard. It's getting you ready for this next step where we are going to, I'm trying to find where my question that talked about how I could use displacement right there. Doing the VT graph work is going to make this really easy to step up to. So that's why we're practicing VT graphs, and it just helps you visualize things as well and get to know everything and how it all connects, right? So on questions like this one here, you're going to draw a VT graph for it as well. Maybe not all, because this one here isn't obviously a VT graph for that one, but so for all number questions or whatever. This one here, I guess, put it like that. Plus VT graphs for those two. You could even do a VT graph for this one, right? VT graphs. That's a good way to describe it as well as part of your words. Path of the ball, 0, VT graph as well. I'll throw up in the air, catch it. Oh, throw up in the air and then catch it. Sketch the path of the ball. Label points of velocity. The vertical velocity is 0. The weird. I think they mean throw a ball up in the air, right? It's going to go up and it's going to go down like that, and then you're catching it. And so they want you to. Well, I already did part of it for you, I guess. The path of the ball. They want you to label points where the vertical velocity is 0. Label points where the acceleration is 0. Okay. So leave that with you. Yeah. Thanks for watching. See you later.